Okay, so we're going to carry on with power a little bit, mainly with a few more difficult questions, and I've got one quite a nice maths question at the end as well, just to refresh you a little bit on energy conservation as well. To just start off with, a sort of electricity or electromagnetism based question. Not that this is something we're going to be covering in mechanics specifically, but it's good to remind ourselves that power is not something necessarily specific to mechanical physical scenarios, but you can also use it for electrical work as well. So within electromagnetism, if you do physics, it doesn't matter if you don't. We've got this property that if you consider a current measured in amps or amperes, and you multiply it by voltage or volts, you will get the associated power rating of that particular electrical work. So considering that formula, and having been told that an amp is actually a base unit, I think maybe I should put the word base here. What is a volt in SI base units? You've got enough information to work it out, considering both that formula and whatever else you know about work and power and energy. Can we express it in terms of base units? Give it a go. So just checking my work. Volts, quite a complex set actually of base units. They are kilograms, meters squared, per second, per second, per second, per amp, right? Or alternatively, we could write it this way, doesn't particularly matter. So you can see why we give them an alternative name. So volts can be defined in terms of these base units, but that is in fact the answer. For one possible way of doing this, we could consider the formula we've been given here. So volts are equal to, in this case, that's not a W for watts, that's W for work. So it's work over amps in this case. And then what is work? Well, we said work was force times velocity. This is meters per second. Force is mass times acceleration. I'm rushing a little bit here, so I'm being a little bit sloppy because I've got an m here which refers to meters and then one here which refers to mass, but hopefully you get the idea. So then mass times acceleration, that's kilograms times meters per second squared. We multiply those two and you'll get kilogram meters squared per second cubed, and then we've got that divided by amps, and you end up with this version here. So I'm just going to do one more example, and then you can try a couple questions from the textbook and then a nice MADAS style question. So in this case, we've got our force now being specifically stated as being variable and as a function. And as you get into more advanced mechanics, it'll be the case that nothing is really constant. Forces, acceleration, these are all really functions of time or functions of other quantities. So we start getting a taste of it here. So we've got our car, mass 2600 kilograms, travels in a straight line. Let's put the car. Its mass is 2600. And when the speed is v, the total resistances to motion are modelled as this variable force. So this resistive force, I guess we'll call it friction, Fr, this is equal to 800 plus 5 times the velocity squared. So as the velocity increases, the resistance is increasing, and it's increasing with the square of the velocity. So hopefully that already gives us some intuition that this is going to really limit the speed at which the car can eventually go. The car has a cruise control feature which adjusts the power generated by the engine to maintain a constant speed of 18 meters per second. Okay, so that's quite a complex scenario if you think about it. You've got variable resistance and constant power already results in variable acceleration, and now we've got variable power. So your acceleration, your rate of change of work has a rate of change. Luckily, it's not going to be too complicated because we're going to be talking about what the situation is at specific instances. But it's just worth keeping in mind that these situations can get rather complex. So this cruise control feature is cleverly adjusting the power of the engine, and it maintains a constant speed of 18 meters per second squared. So we're going to find the power generated by the engine when the car is traveling on a horizontal road. Right, so when it's a straight line, that's fine. So we're on a horizontal road. There's your friction. Let's call it driving force. We know that power is equal to net force times velocity. So let's first find that net force. When V is 18, the frictional force is equal to 800 plus 5 times 18 squared, which is, let's take a look, 2420. So if that's the friction force, that implies the driving force is also 2420, because the net force must be 0, and therefore you're going at a constant speed. I think I might have mistakenly said a moment ago, I was talking here and I said this was net force. I shouldn't have said that if I did. This is, remember, just the force that's producing the power. So in this case, the driving force. So the driving force times the velocity is the power. So that's going to be 15 times 2420, which in this case is, oh sorry, not 15, 18. 18 times 2420, which is 43560 watts. Okay, and then the second scenario is saying what happens if it's at an angle of 4 degrees to the horizontal. So let's just very quickly, let's just do rough sketch because it shouldn't be too complicated. 4 degrees, there's the car. We've got 2600 G's down. I only care about the horizontal forces, or I should say parallel forces. That is 2600 G times sine of 4. Let's be careful now. Is it saying anything about the resistant force changing? I don't think it is, in which case we had that a moment ago as 2420. We've still got our driving force here. And this cruise control, remember, is maintaining a constant speed of V being equal to 18, so that's convenient. So what that then means is, again, the driving force must be equal to all the forces going in the other direction, because the net force is 0. So the driving force must be 2420 plus 2600 G times sine of 4, which gives us 4197. So then our final power is going to be using this thing here, driving force 4197 times the velocity, which is 18, which gives us 75553 watts. And we can write that in here. Okay, that's it. In some ways, you can see that maintaining a constant speed is actually far more complicated than not maintaining constant speed, especially when you're talking specifically about cars, because it's a little bit unnatural. If you have these resistive forces and you've got this specific power rating of your vehicle, there's going to be acceleration and deceleration whenever that power changes. If you want to get a precise speed, it's actually very difficult. It's part of the reason why when you're driving a car and you want to maintain a specific speed, it's very subtle what your foot's doing on the pedal. You're releasing a little, you're increasing a bit, and it's almost like you're guiding it into the speed that you want. It's not quite as simple as just adjusting the press on the pedal to exactly the right degree for the speed you want. It's very much relative to the speed you're currently going at and the friction of the road. But if you've got cruise control, you don't need to worry about that. Cool. All right, so some questions for you to try. Let's take a look. So I'm only going to give 3 questions this time, 2 from the book, which are sort of bog standard textbook questions, although this time we've got this variable sort of resistance to motion or variable forces effectively that depend on your velocity. So see how you do with those ones, and then don't miss the next slide, because the next one's quite a nice looking question, I think. It's not necessarily power, because I think if you're able to do these 2, you should be okay with power. The slide after this one is a nice one on I think conservation of energy, but try these 2 first. Give it a go. You can pause the video now. Okay, and then here, take a look at this one. It's quite interesting. It's a little bit of geometry, a little bit of conservation of energy. I quite like this one. See how you do.